All right, I'm recording. So welcome to the class in software engineering. This is a theoretical class, and what I mean by that is we're going to discuss the theory of software engineering. Not that the class is not going to be a real class. It's a real class. It's not, in that sense, it's not theoretical. But it's theoretical. The material that we'll discuss is going to be theoretical material. We're not going to do programming. That holds true for the lab also. But we're talking about programming. So let me first share the screen and talk a little bit about what's on Moodle. So here is the course. We have the syllabus. I translated it exactly from the Hebrew program. Let's look at it. So, course objectives: students will be familiar with a variety of methods of software development. Classic methods versus agile. Students will know how to identify and solve problems. Okay, we're going to learn some things that you may have already had some exposure to, like class diagrams, but some things that you haven't, like sequence diagrams and initiation document. So here is the outline of weeks. I changed it a little bit from the Israeli program. The end here is based on a book, a new book that I think is good to go over. The book is in the new book that I based the end of the class on. This is for the lab here. Here. The exercises is 20% of your grade. The exam is 80% of your grade. Now, the main book for this course is this Ian Somerville, Software Engineering. So it's quite, this is 8th edition, is 2007, so you can see it's quite an old book, but he keeps revising it. The same man, Ian Somerville, came out with a new book called Engineering Software Products, which is a much shorter book, smaller book, and more modern. So I based the whole half of the second course is just going to be slides from that book. That's from about, no, that's from about, that's from about here, where we talk about, where we're actually cloud-based software and all this agile features, scenarios, and stories. That's all from that book. This is the more traditional part of the course that is exactly the same as the Israeli program. So I changed the course a little bit. I think and I hope it's for your benefit. What else? Here you see the link for the Zoom, and here are my lecture slides. So let's start with the first lecture slide. Software engineering. Can I make this a better view?
Yeah, you could click on the up, that to get rid of the side, yeah. And then next to the 100, 2 buttons to the right, there, and no left, yeah.
That's it. That doesn't do much, but okay.
You could just download it.
You could also make the browser full screen.
Yeah, well, I made it actually. Yeah, you know what? Since I made it, I have it in a different location. I can give you a better. No, not here. Not here. Just a second. Here. Slides. Okay, so software engineering. Okay, the first thing I put here is just to start off with something that confuses people. This is a UML diagram. In other words, this is a diagram of all the inheritance showing diagram of all the types of diagrams that there are in UML. And I want to start with this because a lot of people think that the only thing that's in UML is a class diagram. Here is a class diagram. Actually, all the UML encompasses many types of diagrams. So here, all of them are types of diagrams. There's two main types: structured diagrams and behavioral diagrams. Structure, another way of calling behavioral ones would be like dynamic diagrams that show behavior, show something changing. Structure are more static. So in the course, we'll talk about pretty much just class diagrams in the structured ones. But in the behavior diagrams, we'll talk about activity diagrams, use case diagrams, and sequence diagrams. So just don't tell me that, a lot of students say, oh, you mean the UML diagram? And I'm like, well, that doesn't mean anything. There's many kinds of UML diagrams. So that's just the first thing I want to clarify. Okay, now we'll start with the material. Like I said, there's a lot of theory here. Software. What is software? Software are computer programs and associated documentation such as requirements, design models, and manuals. It's interesting that that the definition includes user manuals. That's software.
Whose definition is this? This is
What?
from the book? This is the definition from the book?
No, this is the definition from the Hebrew program. It might be from the book. I mean, I don't remember. I don't remember exactly where I got it from. Some things are from the, I don't know. But it's not my definition. But look, it also has design models are part of software in a bigger sense. Because if you're a software engineer, you're making a diagram. Engineering means that you're designing something. You're not just you're not just typing code. A lot of times in a company, there'll be somebody who will design and will give you instructions for what he wants your software to do. And you have no idea what the big picture is. You're just writing your little tiny modules, do this little thing, and you have no idea why they need it. And you're just following instructions. So somebody designed the system. He's the software engineer. You, if you're just, following instructions and making a program that does what he told you it should do, you're not a software engineer, you're just a programmer. So actually, software engineering includes design modules, so software includes design models. Software products. So there's two types, and this is actually an important distinction. One is that they're made for a particular customer, like the US Army needs software to run its missile system. Or it may be for general retail market. I'm just reducing it, and it's, anybody wants to buy it can buy it. If they like it, they'll buy it. If they don't like it, then they won't get sold. So essentially, I just said what this is. It can be either generic for a range of different customers, like Excel and Word are generic software, and it can be custom, developed for a single customer according to their specifications, like I said, like the Army. Now, there's a certain kind of software system which is called an information system. There's actually a degree you can get, information systems. You get a degree in, Bachelor of Science in Information Systems, which is I would say it's kind of like a less math and less rigorous kind of computer science. But it's information systems are systems that are designed to maintain data or information. So, for example, like maintain the orders on a website, keep track of their customer base, of your inventory, of your orders. All that is information that needs to be managed. You want to be able to produce reports, documents, how many did I sell of this? When do I need to buy no more? How many of my items that I shipped were lost, and how many came back, and how many, all that information is an information system, it's a kind of software. So components of an information system are these four things. So the people themselves are components of it because they use it, they input data to it. Hardware and the means of production, including all kinds of machines. So anything that, you know, any kind of hardware the system uses is also part of the system. And the data itself is also part of the system. And the software. Now here we're defining software as algorithms for manipulating data. In other words, that's software. It's the method for treating the data, you know, comparing the data, producing new data based on other data. Okay, information system in an organizational environment. So we have, this is like the information system in green. And then we have the people that use it. In the suppliers might use it. For example, you know, the supplier needs to get, you know, get a request, an order form that tells him to, you need to supply us with some more of this item. And then he may supply to the system his receipt, you know, that he his delivery receipt or something. Customers, people that use the system, you know, if they're if it's a library, for example, so the people who take out books are using the system to check out a book. So they're customers of the system. They're not supplying books, but they're customers. Competitors might use the system. We might rent out our system to somebody else, or we may give them access. Regulating agencies, right? So somebody may want to see look at our books. Stockholders, people who own the company may want to check out how much sales have we had, or how many books have we, you know, given out. Now, a system can be defined in these three parts: input data, process data, output data. And then the output can become new input data. So, in other words, data comes in, like a particular book was issued to a customer. Now we process that data. We may put it in various databases. We may add it to certain statistics on how many books were given. And then we have some output. We may have like a document or something. Input can be from people. You know, customer might give information, supplier might give information. Stakeholders. Stakeholders are people who have a stake in this system. So obviously they're the users. They're also the software developers, as they have an opinion about how the system should be made. These are kind of like the people that we would consult when we're making the system. And then, right, the users, the client, if there is a client, in other words, if somebody called us up and said, please make me a software system for my, you know, airplane company, keep track of my flights. So he's a stakeholder if he ordered it, because he can tell us how to do it, how it should be, how he wants it.
Aren't shareholders also technically stakeholders?
Shareholders of the company, of the software company?
Yeah.
Yeah, you could also say that. Yes. Product manager. So this is or owner if the software is sold retail. So this is actually an interesting thing. When I worked at a company, we had a person whose job was not project manager, product manager. Now, what the role of the product manager is, it's usually not, it shouldn't be the owner. It could be the owner, but if it's a very small company, but it should be a separate person. And his job, if it's a retail software, what I mean by retail, I mean that it's made for the general public, it wasn't contracted for. So the product manager, he's the one who decides what the product should have as far as features, what it should do. In other words, the owner may say, I want it to do everything. And the product managers say, you know what, you're going to put too many features on this software and it's going to become cumbersome to use. The ideal version of this software should only have X, Y, and Z features. So he can serve as a limiting voice in maintaining the product integrity and having a product vision and keeping the software to that vision. He's also a interface between the software, the engineers, the software writers, and the owner. Or in other words, the writers may say, we can't do that. That thing will take a ton of time. And he'll go back to the owner and say, listen, we could do that feature, but we have other features that are easier to do and that are more useful. So let's put that one on the back burner and not get to it right now. Now he's in charge of sort of deciding what the product should look like. So he's called the product manager, and he should be a person who's aware of the feel of the shook of the marketplace, of what is out there and what is going to make his product different and better. Now, why it shouldn't be the owner? Because the owner may have unlimited desires. You need another voice who's going to say, wait a second, I understand the technical side of this, and I know better than you, even though you hired me. But you hired me, and it's like, anyway, you hired me to give to limit you, to give you good advice. Okay, stages of the software product. So this is kind of obvious, but there's the birth. Now, what's the birth of the product? There is usually a need for a software solution. So you observed some kind of problem and you decide to fill that need. So you don't just make software for you usually make it for a purpose, because of something missing out there. A software developer is hired or contracted to create the code. The code is delivered to the initiator. The initiator is like the person who wanted the software, who saw the need. He may not himself be a programmer. Then the next part of it is that it starts getting used. The software is installed or deployed on servers. Users discover unmet needs and tell the initiator, in other words, now we're going to modify the software. And the initiator may decide to repeat the birth stage. In other words, he may, there's a new need, so we'll go back and program more. Or he may not do that. In any case, this is the evolution of software. It may advance over time in the use. So death is when there's two definitions of what death is. One definition is when the users no longer use the software. In other words, as long as the software is being used out there, it's not dead. Another opinion is no. Well, once the initiator no longer supports the software, like if Windows says we're no longer supporting Windows, NT or something, or Windows 95, so there may be people still using it, but it's dead in the sense that it's no longer being updated. If there's a hack, somebody finds a way to break it, we're not going to fix that. So that may be called death also. I saw two definitions. Now, a software project has three components that go into making it. This is a weird kind of definition here, but the product has requirements or features. In other words, it has to have something that it's supposed to do, some requirements that it's going to fulfill, and some features that it's going to provide. It has also a time constraint, because a project, when you make a project, you're not just going to say, well, I want this product, I want this software written, and I don't care when you finish. Because if you don't have any time constraints, then it may take too long and it may no longer be useful. So it's going to have time constraints in any project, and it's going to have resources. People who are programmers, it's going to have technology, like certain software that you're going to use to make the software. And it's going to have rules of development. In other words, we'll have certain rules about how we use it. It must be object-oriented, or it must be, distributed database. We have some methods that we're going to follow. Okay. So what is a software engineer? A software engineer is the bridge between the idea and the technical implementation. In other words, the initiator says, you know what, I'd like a software that does this, this, and this. He may not know anything about how to do it, But the engineer will figure out how to get that technical implementation to get there. And he must know the software domain and the problem domain. What we mean by software, well, let's talk about the problem domain. The problem domain is he has to know how libraries work if he's going to make a program. He also has to know the software domain. He has to know what software can do and what it can't do, what it, what are the best ways to do things. So he needs to know 2 different domains. It's important to know, a lot of times they don't know the problem domain, and that can be a problem. In other words, you need to know what especially if you're a product, see, a product manager is usually not a programmer, but a lot of times he has a lot of technical knowledge because he's got to talk to the technical people. So he also should know the software domain, and he should certainly know the problem domain. He should know how library is supposed to work if he's going to make software for a library. Like my wife, until recently, worked for a company that did medical software, not for machines, but like for emergency medical assistance, and for organizing. It was actually an information system to organize all the workers and stuff. So the person who started the company worked for MADA, worked for a emergency medical company. So he knew the domain. He's not a programmer, but he is essentially the product manager. He is the product manager, even though he was one of the owners, because he knows the problem domain. The challenge is to learn new and diverse disciplines and processes. In other words, if you're this software engineer, so you have to keep track of all the software, and if you learn new problem domains, you may write something for a library, then a year later write something for an airplane. You're going to have to keep track of all these new areas. You also have to be able to extract an abstract model for the problem. In other words, you have to see the problem, see a solution, and be able to make a model of it so that you can explain it to other people, so that everybody will understand what the solution and what the process and what the engineering solution is going to be. They didn't see. The worst thing is that you have misunderstandings among the team that is creating the software. So I could essentially say that the purpose of the models is to clarify exactly what you're going to be doing, so that everybody in the team should know what is being expected of them. And you shouldn't have a situation where somebody writes something and a month later you find out that what he wrote is completely wrong and not what you wanted. Given discipline-specific information. In other words, it's not just any model. It should be according to the discipline called software engineering. You need to design an ever-evolving solution that realizes the abstract model. In other words, it's not enough to have a solution that solves the problem. It should be a solution that is capable of evolving, that you can add easily to it, that you shouldn't have to rewrite the whole thing because you want to make one change. So now we can talk about modeling. You create a model which abstracts the system using a diagram. So this is why we make diagrams, to give an abstract view of the system. And like I said, so that everybody would know what we're doing. We include the major features and may ignore other features even if they are important. So as we don't have to have every single thing that the software does in the model, because we want to get the broad strokes of what we're doing. The model will simplify and make it easier to understand a complex system. Now, what is the software process, or a software process? A set of activities whose goal is the development or evolution of software. Okay, that sounds like a definition. There's a bunch of activities to create software. And some of these activities are the specification of the constraints. That is what it's supposed to do, by when it's supposed to do, what are the constraints, how much memory. When they make a new cell phone, they have to decide, well, I want it to be able to run fast and good on only 8 gigabytes of memory. So we have some constraints because we want to keep the price down. We have to develop it. We have to actually do it. Then there might be validation by the client. Somebody once said that Bill Gates has the largest, this is back when Windows was very unstable. So they said Bill Gates has the largest quality assurance staff. The quality assurance staff of Bill Gates for his Windows is all the people that buy his software, because they are validating by the clients are validating whether the software actually works and sending him bug reports. And then there may be which is a joke kind of, because it should be that the client gets it and it works. Then there's evolution. In other words, improvements, changes. Obviously, you're all aware of versions, new versions coming out. Why do we need to do engineering? So it really goes back to these large government software projects. And like, sending a man to the moon, or missile systems, or a lot of it's military. They were delivered in unusable states or abandoned midway through the development. I don't think I included it here, no, but there were some statistics that I saw, a huge percent of software was just abandoned. It was just it was just so badly done that in the end, the person who contracted for it, the government agency that contracted for this software, just realized they couldn't use it and just threw it away and started over, or, hired a different company to write their software. So we don't want that kind of things to happen. We want to have, we want to plan things and have it work right. And the question is, why can we design bridges correctly, but we can't design software correctly, right? So there's a few reasons, actually. Bridge design is fairly unchanging. But the more important point, in other words, so we figured it out once and we sort of know how to do it. But the other thing is, errors have serious legal consequences. People could die and we could get sued. Software, people don't die from software not working. Well, actually they do. I actually believe that the planes that crashed, these Boeing 737 Maxes that crashed, was because of glitches in the software. If the software, from my reading about it, the software was written in a bad way, and it caused errors to not be able to be handled by the operators properly. In other words, the operators were aware of the errors and they couldn't fix them because the software didn't let them. Software also changes, and errors are often ignored or covered up. So you can hide an error more easily than you can in a bridge. And also, you may change it midway through. In the middle, you may say, "Oh no, we need this," and you don't do, and that can cause it to not work properly. Now the design was already designed for a different thing. If we can treat software like bridges, we will have a better product. So the goal is to create an engineering of software, just like we have an engineering of bridges. That would be the goal. That's what software engineering is. Turn software into a thing that can be engineered and done right and not have errors. That's the theoretical goal. Whether we're going to actually get there. Now, this is a joke I remembered reading 20 years ago, and I found it again, and I'll read it to you. If cars were like Windows meaning the Windows operating system. You guys know this one?
No.
What? Daniel, you heard of this?
No.
Yeah, it's before your time. But because it's when Windows was very unstable. For all of us who feel only the deepest love and affection for the way computers have enhanced our lives, read on. At a recent computer expo, Comdex, Bill Gates reportedly compared the computer industry with the auto industry and stated, if GM had kept up with technology like the computer industry has, we would be all driving $25 cars that got 1,000 miles to the gallon. In other words, the computers keep getting cheaper and faster. In response to Bill's comments, General Motors issued a press release stating, if GM had developed technology like Microsoft, we would all be driving cars with the following characteristics. For no reason whatsoever, your car would crash twice a day. Every time they repainted the lines in the road, you would have to buy a new car. Occasionally, your car would die on the freeway for no reason. You would have to pull it to the side of the road, close all of the windows, shut the car off, restart it, reopen the windows before you could continue. For some reason, you would simply accept this as normal. Occasionally, executing a maneuver such as a left turn would cause your car to shut down and refuse to restart, in which case you would have to reinstall the engine. Macintosh would make a car that was powered by the sun, was reliable 5 times as fast, and twice as easy to drive. But it would only run on 5% of the roads. Well, you guys don't know what that means, but the Macintosh, I don't know if the apps, certain apps can run on Macs, and like a lot of stuff. It used to be It used to be that you could only buy Apple software for Apple computers, and you couldn't buy any third-party software. That's what they mean by that. The oil, water, temperature, and alternator warning lights would all be replaced by a single message: this car has performed an illegal operation. The airbag system would ask, are you sure, before opening. Occasionally, for no reason whatsoever, your car would lock you out and refuse to let you in until simultaneously lift the door handle and the key, turn the key and grab the hold of the radio antenna all at the same time. Every time a new car was introduced, car buyers would have to learn how to drive all over again because none of the controls would operate in the same manner as the old car. You'd have to press start button to turn the engine off. So that's a joke, but the point is, why I brought it up is because you see that a car has certain features that are well engineered. Like you can get into any car and immediately start driving because there's a uniform interface. Everybody, everybody makes the pedal, in the same place. The gas pedal is always on the right and the brake is always on the left. Nobody makes cars in other ways. I mean, in England, they have different cars, but basically all cars run with the same interface, whereas software doesn't. We don't have like a uniform interface for software. Truth is, planes do not have uniform interfaces sometimes. I mean, like if you want different switches can be at different locations. So, but cars are an example of something that's very well engineered because it doesn't do all these bad things that software can do. Oh, here we go. This report of 1985, 39% of software projects were on time, in budget, and fully functional. Only 39%. 43% were late or over budget or lacking a feature. And 18% were canceled or never used because they were just too badly made, or they were canceled. So this led to the introduction of software engineering, this problem, where we're going to try to have a systematic approach to software development. We're going to try to use some principles and have methods and tools and procedures that will ensure quality. We're not just going to let anybody do whatever they want. I mean, that's the ideal. Now, in 2015, they listed factors leading to success. The Standish Group, there's some kind of a, think tank, and they came up with what makes a project successful. So, executive sponsorship of the product. If the top executives are behind the project, then it'll more likely be successful. User involvement. This is important. That you have some people who use the software talk to you and tell you what they want. You have skilled resources. Now, as your staff, your programmers are skilled. If they're not very good, then you're going to get bad things. You use a standard architecture. You don't try to invent a new design. You try to use a previously used architecture. And then we have this agile process proficiency. Agile process proficiency means that you're constantly reevaluating what you're doing. You're changing sometimes what you're doing, and you have a system developed that allows for changes while you're making it. And you use milestones, which means you say, I want to have this feature by this date and this feature by that date. Project management expertise. So you have the people who are managing the project have been successful in the past. And a clear business objectives. You know why you're making this project. You're making it to, what goal is it going to provide? What business objective is it going to have? How is it going to help you make money? Now I added some things here. There's a general concept called a software requirement specification, which is a description of a software system to be developed. And it's similar to a business requirements specification. It lays out the functional and non-functional requirements that, in other words, it tells you what the system is supposed to do before you do it. As you write down on paper or on the computer, but you write down something clear that says what your goal is. It may have use cases. We'll talk more about use cases later, but use cases describe how a user will use the different cases in which the user will use your software and how he'll interact with the software. So this is a software requirement specification, an SRS. It's the basis for an agreement. This is also important. It's like a contract between all the people involved, the customers, the contractors, the suppliers, how the software should perform. Now, they're going to pay me money to make this, and I'm going to make it according to these requirements. And I may built in, you can have you can have 3 changes of, this and this amount of code lines. And anything more, you have to pay, $1,000 a change. It'll be a contract that says what because otherwise the client will just say, oh, no, I want this. Oh, I want this feature. Now I want one more feature. Say, wait a second. In the beginning, you said you only wanted these features. That's all you're paying for. So you may allow him, an extra couple features, but you'll have a contract. Right. And sometimes if it's not contract, so in the parentheses, it mentions if it's not a contracted thing, in other words, it's what I call a software product, or what you could call a generic software, then the marketing and development divisions of your company may tell you what the features should be, because they're the ones who decided what the market wants. Software requirements specification is a rigorous assessment of requirements before the more specific system design stage, and its goal is to reduce later redesign. Right? We don't want to do redesign. We don't want to have to rewrite what we did, or redesign is even worse, changing the whole method of how we did it. Should also provide a realistic basis for estimating product costs, risk schedules. Used appropriately, software requirement specifications can help prevent software project failure. So in other words, you say what you're going to do before you do it, and you get everybody to agree and sign off, and then you know that what you're going to produce is what is wanted, and you're not going to by mistake make the wrong thing. The software requirement specification document lists sufficient and necessary requirements for the project development. And there's all the things it's supposed to do. How do you get these requirements? You need to have a clear understanding of the products under development. You need to know what you're trying to make. This is achieved through detailed and continuous communication with the project team and customers throughout the software development process. You should be talking to somebody you should be showing them what you did. In fact, sometimes what you do is you write a website that looks like the software, and as you make a graphical user interface, a GUI, that has all the buttons that you want it to have and all the features, but none of the buttons do anything yet. It's just to show you how the user should use what is. When you see all the buttons, you can say, oh, wait a second, you don't have a button like this, or wait a second, why do you have this button? I don't want that. So even before you program anything, you can show him. It can either be, just a drawing, or it can be computer drawing, or it can be like a HTML button type thing. But some kind of mock-up of how the thing is going to look before you build it, to make sure it's what everybody wants. But that's different. That's in addition to an SRS. An SRS is more of a paper word contract. Typically, an SRS is written by a technical writer, a system architect, or a software programmer. It could be by a programmer, but like I said, it's a document that could even be written by a technical writer. So there's 2 kinds of quality things that we can think about when we talk about software. One is external quality, which is how is it easy or to use for the user? How does what's his user experience? Then there's internal quality. Wait a second. Internal quality is like how the design is. Like sometimes a software programmer will say, like, I want it's more elegant if I write the software in this way than if I write it in that way. The user will never feel the difference, but for him, it's easier for him to, it's a better written in the sense that it's easier to manage in the future. It's easier to alter and change. So from the perspective of the programmer, it's higher quality because it's easier for him to update it and to fix bugs and to not have bugs. So those are 2 different kinds of quality we can talk about. Now, what are external characteristics of good quality? So, in other words, what is the user looking for? What are these external, in what we call external quality? Well, it should really be called characteristics of good external quality. I guess that's how you should change that. Correctness. The system should not reflect misunderstandings of the specification, neither in design nor, wait a second. I got to fix that.
What is this talking about? The external, whatever the characteristic of good external quality or whatever it's going to be.
In other words, external quality we just explained is what the user feels. Does he feel it's good software? What makes software feel good, feel like it's good for the user, from the user's perspective?
So basically user friendly
Yeah.
software.
User good. Right. It could be more than just user friendly. You'll see in a minute. Right? View present. So correctness. It should not reflect misunderstandings of the specification. In other words, it should do what the user wants it to do. If it was contracted for, then it should do what he contracted it to do. If it was bought, it should do what you would think you should want. Usability, ease for users to learn the system, ease for users to use, for users, ease for use for users. In other words, it should be easy to use and easy to learn. It shouldn't be that I have to hunt for this button that does what I want, a simple thing to do. It takes me 10 years to find this button, and finally I can do what I want to do. It should be easy to use. It should be, correct is one thing, but it could be that it's hard to find. Efficient, that the system should not run slow, right? I don't want, my system to run slow. Reliability, the system should work even if there are minor faults. In other words, if something goes wrong, it shouldn't just cause everything to crash. It should still work mostly. If you have a 1% failure, it should continue working 90% of the 99% of the time. Integrity. Prevent the system from being used. In other words, it should be safe. It shouldn't be that anybody can start using it illegally. Robustness. Well, this is similar to reliability. It should handle, in other words, robustness here, but I specifically said input. If I put in the wrong thing, it should continue working. I shouldn't be able to break it just because I gave it the wrong input. So those are things that the user will feel. What about internal quality characteristics? So this is what we're talking about. This is what the software programmer is looking for in the software. When he comes to the, you hire a new worker and he comes and he says, my God, I can't work on the system. It's terribly written. What does he mean? Well, he means that one of these 5 things is wrong. That scalability. So scalability is an important concept to know in general. It means that when I add more resources, I get better results. Sometimes you have a system, you give it twice as much, you increase the memory by twice, and it still runs about the same speed. It doesn't hardly get any better because it wasn't able to utilize that new memory properly. So scalability means that as I add more resources, it gets faster. This is a problem. This is a very big problem. A lot of times people write software, it happens all the time, and it's not scalable. They wrote this great software, like Facebook was amazingly scalable. As more and more users came on the system still worked. You can imagine that you write a system that it works great for 100 users. Once you get up, 1 million users, it just doesn't work anymore. You can't fix it. You have to start it. The design is designed in a way that when you have that many users, it just can't work. It's going to be, it gets like exponentially slower as opposed to linearly slower. Right? Scalability, it should be a linear function. As more users use it, it should get linearly slower. If it gets exponentially slower, then it's not scalable. So that will be one thing. But of course, the user won't feel that, unless it gets to large scales. But that's an internal quality. Maintainability. That's what I was talking about before, mostly. That you can add new features without having to rewrite everything.
Why is that not the opposite? Shouldn't scalability be adding new features being able to add new features without running into problems. Like you're able to scale it with your, I don't know, whatever. Never mind.
Scalability usually means without changing the system, as more users get on, how much slower does the system get? And can I solve that slowness by adding more resources? In other words, if my website is getting slow because I have 1 million users, so I just put another server up, and now all of a sudden it gets, it gets twice as fast. And then another million, then I get more users, I put another server up. I can keep on just increasing the number of, but if at a certain point I add another server because I thought I need to add another server, it doesn't help. And I have 2 more servers, it's still slow. Then my system wasn't scalable. I wasn't able to make the system, I wasn't able to expand the scale of the system to accommodate the expanded use. Even though I expanded it, it didn't help. That's scalability. Maintainability is that in the code itself, I want to add a new feature. I want to make it that all of a sudden I can add a button that does some new thing. I want to add a new drop-down menu. And when I add that, is it going to require me to do a lot of programming or a little programming? That's maintainability. Flexibility is expanding the system for other uses or other environments. Example, by having modular components. This is similar to maintainability, but it means like flexibility. Can I take my software that was designed to run a garage and maintain its inventory of the mechanic shop, and now use the same software with a slight modification for maintaining a library? A lot of times companies do this, where they have a set of software, and if they get a new client that needs it, they just add a few modifications, and now it's software specific for their company, and they can write, they can alter the software in such a way that this is good planning. You write your software for your company, and then all of a sudden you realize this happened to a company I worked for also, that they were writing software for their own use, and then at a certain point they realized we're not making enough money. Let's sell our software to other companies that do similar things. So then they hired more programmers, and they became a software company where they took their in-house software and modified it, and they only had to do slight modifications to enable it to work for other companies. And each time they would get a new contract, they have a sit-down meeting, and they would decide what features they want, and they would alter the core software to fit the new need. That's flexibility. Portability means that you can use it on different operating systems. In other words, it doesn't use features that only exist on a certain operating system, but I can, change a few lines here and there, and now it'll work on a Macintosh. Reusability is similar to flexibility, that code can be used in the next project. In other words, I have the ability to reuse some of the software for this project for some other project. Okay. Oh, so what did I say here? If I put you guys to sleep?
Nope.
No.
No,
Okay.
are we supposed to be sleeping?
No, you're not. I just want to know that I'm talking to listening people. I mean, I wrote very detailed slides, so it sounds like I'm just reading from the slides, but that's because I wrote detailed slides. Book Challenges is a book called Challenges of Software Engineering. And in that book, it's written the following quote: software engineers are aiming at optimal designs, but quantitative criteria for optimal software design are largely unknown. In other words, software engineers are trying to have the best design, but we have no idea what constitutes the best design. We have no quantitative criteria. Optimality criteria appear to be mainly based on judgment and experience, which are intangible factors. In other words, somebody will just say, oh, this seems better than that. It's like saying, this bridge looks better than that bridge. It seems like it's better. But we should have a way of judging. We should have a way of, stress testing things and saying, oh, no, this is better. We should want some objective criteria. So we need to define what we want to be the above quality parameters. In other words, really, we have to have some kind of quantitative criteria. But whenever, I mean, I don't want to disappoint you, but that's like a theoretical goal. I don't think we'll get there. I mean, I don't have a plan to get there. What is software engineering? So here's some definitions, different definitions. So it's the investigation of an orderly method from the idea stage to the development stage for producing an accurate, valuable, and high quality software product. In other words, it's not just creating a software product, it's having a method. It's creating, it's investigating the best methods for creating the best software. That's what software engineering is. Now, in the Pressman book, it says the establishment of use of established engineering principles to produce an efficient, affordable, and reliable software product. So that's also true. You should use some kind of engineering principles to produce that good product. There should be some principles. Well, that's if you're investigating, so you're going to find some principles, presumably. IEEE is like a standards organization. The implementation of a systematic method based on rules, which means it's disciplined. It follows a certain discipline. So systematic method, which can be measured quantitatively, like we said before, quantifiably. We can decide how much better is this software than that software, which can be measured quantitatively for the development, operation, maintenance of software product, and research into the above. Okay, so you see, it's like a field of inquiry, software engineering. What is a project? A project is an organizational campaign to produce a unique product with rigid time and resource. We kind of said this already. You should have some kind of constraints, and it's a campaign. It's a to produce a certain product. Now, the life cycle of a product. By the way, this is my shortened version of the Hebrew slides. I cut out 30%. So, but I can imagine how long it is in Hebrew. Commonly used terms refers to the stages of So these are commonly used terms, or I don't know if they're terms, but these are the stages of a project. First, we talked about this already, I think. First, you recognize the need. Then you have an idea for a solution. Then you develop the solution. Then you actually deploy the solution. You develop the solution, means you created the solution. Now you have to put it on the computers that are going to use it. That's deployment. Then it's on the computers. Now you use it. Now you improve it and modify it. And the life cycle ends when it's no longer in use. So we already said this. I don't know why it's repeating, but I guess I didn't notice that it repeated itself. I would have cut that out. Maybe. Design process, or maybe it's add something a little bit. Design process, SDLC, structured development life cycle. I mean, you have no idea how these exams are sometimes in this class. Sometimes the exams are things like, which of the following is not part of the life cycle of a project? And they'll list some things, and you have to pick out the one that's not part of the life cycle of a project. So yes, you have to know this stuff. I will modify the Hebrew test, though. You'll not get the exact same Hebrew test because I'm going to teach some stuff that's not in the Hebrew, and I'm going to remove some of the things that are in Hebrew. Anyway, so this SDLC, Structured Development Life Cycle, it defines the stages to develop the project, what to do in each stage, how to do each stage, what will be created in each stage, and how to move from stage to stage. How do you know that you finished one stage and get to the next stage? What are your indicators to move from stage to stage? Okay, so now we're talking about the first model that actually is a software engineering model. And this I didn't write this. I think I summarized, I took snippets from Wikipedia, but because I didn't like the Hebrew definitions, because this is actually, So the first formal description of the waterfall model is often cited as a 1970 article by Winston W. Royce. Now, actually, it's funny, in the Hebrew, he wrote Jonathan Royce, but it's Winston Royce. Although Royce did not use the actual term waterfall in that article. In other words, people say that he invented it, but he actually never used the term. Royce presented this, so a lot of people say, oh, in the Hebrew side it says Jonathan Royce invented it in 1970, but really it was Winston Royce in 70, and he didn't really name it that. Royce presented this model as an example of a flawed, non-working model, which is how the term is generally used. In other words, it's what you call a straw man argument. You heard of this concept, straw man argument? You say, this is a model, and then you explain it, and then you say, let's talk about what's wrong with it. I'm just explaining it so that you can show you what's wrong with it and how a future model should be different, how the good model should be different. But actually, ironically, it became a model that people used. Before I go on, let me just say what it is more or less. The idea of a waterfall model is that once you're in that barrel and you go down the waterfall, you can't go back up again. Whatever you fell down, you're now at the lower level. You're never going to get back up. Now you keep going down the river and you fall down another waterfall model, a waterfall. The idea is that you only go forward and you never revisit things that you've already done. So the opposite of this would be to revisit things. In other words, waterfall model says, design the whole system, have everything, every feature worked out fully before you start programming. Figure out every single thing you want to have, make sure the client wants it, have him sign a legal contract, that's what he wants, he's going to pay you, have an exact date of when you're going to finish, and then hire the right number of people so that you can finish by that date, and produce the thing, and have it all planned from the beginning. So that's called a waterfall, because you can't go back to the top and say, wait a second, let's add a feature, let's change the design. No, you finish the design stage, you're never going to revisit the design stage again. So this is called, and it's an example of a flawed non-working model, which is how the term is generally used. The earliest use of the term waterfall may have been a 1976 paper. Fine. In 1985, the United States Department of Defense captured this approach in a document called DoD, Department of Defense. I think STD might mean standard. Anyway, their standards for working with software development contractors. In other words, you want to do a project for the United States government in 1985, you have to follow this document. Right? Governments can't just hire somebody and he'll do whatever the hell he wants and hopefully it'll work out. They hire big companies that follow procedures, they have contracts. You can't work, the way, what's his name? Who wrote Facebook?
Zuckerberg?
Yeah, Zuckerberg. The way Zuckerberg wrote Facebook, you can't, work with the Department of Defense. You got to write a contract, have everything all up front. So they wrote the following. The contractor shall implement a software development cycle that includes the following 6 phases. Software requirements analysis. That means you analyze what the software should do. You figure out, you analyze the reality in the world that you're trying to solve, and you talk to the pilots of the plane and figure out what they want their software to do in their plane. Then you come with a preliminary design, then a detailed design, then you do coding and unit testing. Then you do integration, where you actually install the stuff and make sure it works on the plane, and then you test it. Now, this idea means that you have a software requirement analysis and a preliminary design. In other words, once you finish those things, you're not going to go back and talk to the pilots again. In the software requirement analysis stage, you talk to all the stakeholders, figure out what it should do, and you're done. You're not going to go back and ask them again. We don't move upstream. We don't change design once it has been written. What do I have there? Once it is done, because it is expensive to do that. Is we don't want to redesign. So therefore, in other words, what I'm pointing out here is that the Department of Defense essentially adopted the waterfall model. And here are the stages of it, like we just said, pretty much. system and software requirements captured in a product requirement document. That's the SRS that we just talked about, right? A product requirements document. We call that a system requirement. What did we call it? SRS? Software requirement specification. And now we're calling it software requirements, fine, in a product requirement document, but fine, as a system specification, system requirement specification. Then an analysis resulting in models, a scheme or a schema, business rules, how it's going to work. Then a design resulting in the software architecture. Then the coding and the implementation, development, proving and integrating the software. Then testing stage. We don't have. It's interesting. There's not the integration. You don't see the integration stage here as we did before. Here we had integration before testing. Slight differences. Testing, the systematic discovery and debugging of defects. Operations, installation, migration, support, and maintenance of a completed system. They assume that once you tested it and you now install it, there are going to be no bugs. Of course, you could have testing again once it's installed. Stages 1 and 2 are sometimes combined into one stage. Because, right, the model, creating the model, notice the first part is like talking to the people and writing a document. And then you write the model, but you could call that all one stage. Advantages of the waterfall. Easy to plan, right? You're not constantly replanning, so it's sort of easier to plan, easier to manage. Managers like it because they can say, okay, have we got the design done? Have we got, they know where we are all the time. If you're constantly redesigning and changing things, they never know if you finished anything. It's easier for the dim-witted manager to manage something that has clear stages. Stages are clearly separated. They have finished products by each one, right? At the end of the first or second stage, you have these documents and these designs, and they're there. You can show that you're meeting your target dates. Everything is documented. We know exactly what we were supposed to do from the beginning. Nobody can say that we didn't do it right. We have it all written down. Government bodies like this system because you can contract out software and have an exact contract. You know the price tag. You can compare bids between competing companies. If each company says, well, let me start, I don't know how long it's going to take me, I don't know how much it's going to cost. Well, how am I going to, I can't actually work with a company that says that to me because there's law. The laws of the countries is that you have to have a competing bids and you have to take the lowest bid. There's like rules. And I can't have if there's no bid, if there's no actual number. So he has to have, an exact plan and know exactly how long it's going to take him. And that's better for government bodies. Disadvantage of the waterfall. Takes a long time to develop this way. Now, it's the other way, you can just start programming right away. And if you see you made a mistake, go back and change it. Here, before you can even start programming, you got to do all this analysis and documents and designing. So it's a long time to develop. There is little contact between the consumer and the developer after the initial requirement. In other words, in the beginning, they contacted each other, they discussed things, and now they just go and finish their product, and they don't go back and talk to them. So the customer, there could be a misunderstanding, and the customer could be disappointed. And you only get the system at the end of the process. You could be working a long time and you have nothing to show for it. Only at the very end you're going to have something. Whereas if you just rush ahead and start writing stuff, you'll have something to show. Also, testing is held to the end. And you might find that at the end, nothing works. If you're instead of testing all throughout. If something was misdesigned at the start, you're doomed. It'll be hard to go back and change it. You're not allowed to. You're not supposed to. And there's a lot of uncertainty about whether it will be a good product because you haven't been testing all along. You don't, you think it'll be good, but you don't really know. cost of correcting an error. So if the error occurs in the very beginning, it's 1 times something.
Is it still the waterfall?
This is for the waterfall. Well, yeah, for the waterfall. But in general, anything, you might repeat this process. Yeah, basically it's still the waterfall. In other words, in the strategy, analysis, and design, it's still relatively a small factor that it increases the cost of your product. But when you've already got to the build or transition or production state, it's going to start costing a lot more to fix an error. You'd rather find it in the beginning. It's generally true of any project. This is a project lifecycle. This is really true of any project. It's always going to cost more to fix things after you've finished, after you're in production. When to use waterfall? When the system is very fixed and certain. As you know that you're going to have one thing, you're not going to have lots of changes. You know, Facebook, probably, you know, there's going to be a lot of changes because you have lots of users, and why not change them? When we know the exact technology we want to use, we know exactly how to use it. We know what kind of hardware we want to use. We know what language to write in. Everything is defined for us. If we have a large team and people with knowledge may leave and new people may join and need to learn the project, having everything written down and documented prevents a loss of information and shortens the time it takes for new employees to become productive. So having everything written down is a big, it's a big problem in places they don't have things written down. Some guy gets a better job offer and quits. And now he was the brains behind the whole thing. Nobody else knows how the system works. Don't you want to have everything written down? If you have a large team, you may lose a lot of people. You know, there may be a constant flow of people. They need to be able to read some documents and figure out what the project is and what they're supposed to be doing in it. So it's good to have things written down and clearly written down. Also, if we spend a lot of time in the design stage, we may find all the bugs and not have to deal with them later and save money by finding them early. If we just start writing, we may have a terrible bug that we didn't notice for a long time. And now we have to go back and redo everything because we didn't spend much time designing. So there are actually advantages to using this system. But of course, there's the disadvantages, like we said, when not to use it. So don't use it if you expect a lot of changes coming along the way. You don't have a client like the United States government. You're just producing a generic thing to sell to whoever, to the market. And you may see that it doesn't work. You may see that it's not so popular, and you want to change things all the time to make it more popular. So expect a lot of changes. All that designing is not going to help you much. Or if you're charting new territory, you don't know how to design it because nobody's ever done anything like this, and the design for it is not clear. Clients may not know exactly what they want.
So that's like if you're trying to copy like a program, then this is good.
What do you mean copy a program?
Like if you're trying to make an exact replica of another program that already exists.
Yeah, then
you basically know all the designs.
Then you may as well use a waterfall design. You know the design already. You have that already, yeah. But here, if you're charting new territory in the sense, you know, you're using new hardware that nobody's ever used, you're doing a kind of thing that's nobody ever thought of doing anything like this, and the design is just, you know, it's clear that you're going to be wrong about your design. As you work in it, you're going to discover better ways to design it. So your initial design may be worthless. So don't spend a lot of time on it. I mean, obviously, you always have to have some initial design. Question is how much time you spend on it. Clients may not know exactly what they want until they see the final product. And then they say, oh, no, that's not what I wanted. I want something else. Says, your client himself is wishy-washy. So then you're not going to use this. The designer may overlook some edge cases, and so you have to redesign it anyway. In other words, your designer isn't so good. It's not so experienced. There's lots of edge cases that it's impossible to think of. So you better have a system, better have a method that allows for easier. There's no sense in wasting a lot of time designing if you're going to just have to redesign anyway. So there are what we call agile methods. And the basic concept of agile methods is that you iterate and you redesign all the time. And resign all the time, that's not right. Don't resign all the time.
You also had resign in the previous slide,
Oh yeah?
last line at the end.
Oh yeah. I guess I've been losing a lot of chess games. Is that how you spell redesign?
Yeah.
Yeah, okay. Thank you. Here. Okay, wait a second. Oh wow. We're getting near the end. Believe it or not.
We're doing like a break at 4 kind of thing, or?
Yeah, let's have a break. But I mean, when we get to the end of this set of slides, we'll break. When to use it. When not to use it. So we have instead what we call agile methods. Now, agile is also like it's very confusing because there's a particular method called agile. But then there's also agile methods. In other words, in general, using the word as an adjective, as just agile in the sense where we quickly can jump from one thing to the other. We can go from back and forth between design and implementation, design and constantly redesigning and constantly implementing. There are several agile methods. Scrum is one. I'm not sure about that sentence, but Scrum is a lot of time is part of the official agile method. Part of it is Scrum. We'll talk about it more later in the course, but the basic idea is, well, you have features. Each person, says, "I'll do this feature." You work as a team doing different parts, different features, and you reassess the design continually. There's also the Scrum. Scrum is also, I don't think I like this sentence. Scrum is not an agile method. It's really part of the agile method. Scrum is like you have in the morning, you have a meeting where you say everybody announces what they're going to do today for the project. And you may even have certain tasks that need to be done. And there may be like 20 tasks and 5 workers. And a worker will say, "I'll do task number 1 and 3." And this one will say, "I'll do 7 and 2." And each one sort of commits to doing certain tasks. And as they commit, they move. One way of doing it is actually with physical Post-it notes on the board. You move them from, need to be done, working on, finished. And so you take it and you actually physically paste it to the column of working on. Maybe even write your name on the Post-it note. And then when you finish, you walk up to the board and move the Post-it note to finished. That's the Scrum concept, as far as I understand. I mean, that's what I did in a company that I worked for. Agile incorporates that and other things too. So there are several agile methods. Scrum is one. I don't like that sentence. Requirements may be defined by fixed time and resource requirements. In other words, I'll finish this feature in 3 days, and I need 2 workers to help me. That would be resources. We may need to produce something by a certain time and be forced to remove one of the product features to meet the time requirements. In other words, we also can have like this reverse kind of situation where every feature slows you down. If you're not, is actually, I don't know if I mentioned this here. Yeah, here, look at this, Brooks Law. This is very interesting. Adding manpower to a late software project makes it later. Now, there's this very famous book, at least it was famous. Yeah, I don't know if it's anybody who is like an old timer in programming. If you ask Eitan, your software teacher, he'll definitely know this book, The Mythical Man Month. it was like the book of like philosophy of programming in the 80s. And even the beginning of the 90s, the 80s mostly. So according to Brooks, an incremental person, when added to a project, makes it take more, not less time. Why? He needs to be trained. Training him drains the time of the other workers. He will likely introduce bugs into the code, which will require more time from other programmers to come and fix his bugs. They didn't even understand why they were a bug. Right? In other words, you hire this new person, now you got to train him. So the good workers are having training, are wasting their time training him. The good workers are going and fixing all the mistakes that he made. So what's the solution? Removing features is a better way to hurry the project along. You just say, well, we want to get it out. We're not going to do this feature. Which features can we get rid of? Which features will make the project finish quicker? Just remove features. So that's what I mean when I say we may need to produce something by a certain time and be forced to remove one of the project features to meet the required time. And we're not going to add more workers. That's just going to slow us down. Later, we will add the feature and make another release. This is the Agile method. In other words, the first method, you're not going to see anything until it's all done. We're going to give you all the features you asked for, nothing more, nothing less. This says, no, we're going to remove features sometimes if we want to get it finished. And then we'll add them later with a new release. This is obviously the way that things are working nowadays, mostly. I mean, things that you guys are using. You guys are not government bodies, but government bodies may not work this way even now. We want to get something working and out the door as soon as possible, right? Because we want to make money. In Waterfall, the requirements are fixed, and we may have to add time or resources to meet those requirements. That's why the book is called The Mythical Man Month. A man month is like how many man months of work, man per month. If this feature is going to take us 6 man months, and we want to get it done in a week, let's hire 4 times 6, 24 people. We'll get it done in a week. You know, it's like if it takes 1 man an hour to dig a hole, how long does it take 2 men? The answer is still an hour because they're getting each other's way all the time. So, but that's why it's a mythical man month. On a mythical level, on a theoretical level, you might say add more workers, get it done faster. Not necessarily. So that's the waterfall method says, no, you got it. There's no choice. You have to, if you have a fixed time schedule, you've contracted to get it produced by this date, and you've contracted to have these features. The only variable is people. You can hire more people and get it done. And of course, you might produce crappy software because the people don't know what they're doing. But there's a reason why they're doing what they're doing. Why the waterfall requires that of them. So here's just a picture of the same thing. Waterfall, you define, you build, you release, you have something of value. Here is small. Here your risk is small, but because you haven't done that much yet. But then if you find a flaw now, you have a tremendous risk. In other words, because you're gonna have to go back all the way to the beginning. Here is the Agile method. You define, you build, you release. Define, build, release. Define, build, release. You're constantly redefining, adding a new feature, so it requires new defining. Of course, you can see logically that in a system that's agile, you're going to want a software framework, a software design that allows the addition of features easily. You want a flexible design. We talked about that before, flexibility. You want a very flexible design so that you can, in fact, do this redesigning. You want to be able to just redesign a module, not redesign the whole system. Here, I mentioned this. For Bill Gates, the users are his quality assurance. Criticism of difficulty of agile. So that's one thing. In other words, you release something here, but it doesn't really do much, and the people are going to complain, and then you release it again. In other words, you're releasing something that has less value. Notice that the star here is light. It only gets dark It only becomes really valuable towards the end. The early releases are not so valuable. Now, there's a key point here. The releases may be internal or external releases. There's a concept of an internal release, which means I released it. Now I'm considering the software usable, but I'm not actually selling it yet. But I'm releasing it internally to be tested. Remember, in the waterfall, they don't test until the whole thing is finished. Here, I will release it internally so that it can be tested. Let me add that. In Agile, we still need a good and expandable design. That's what I was saying. It might be harder to design a system that can be implemented piecemeal. In other words, you have to have a design that it's maybe a hard thing to design a system that you can add parts to. This we mentioned. And again, this idea of the criticism is essentially a criticism of the waterfall method, the title of the book. In addition, as other, I never read the book, but I'm sure it has other things to say about software. By the way, a good book for you to read about software, not about software design, but about good programming practices, is a book called Code Complete, published by Microsoft. It's a book. It's been around for a while, but it's been improved and edited. It's still a good book to read. But it's not more on the design level. It's more on the actual like lower level coding. All right, so we'll take a break now. When are we officially? Let me stop recording. Stop share.